All right, so you may have noticed that the drinking fountains in the school have been turned off, mainly because of COVID-19, but we wanted to solve this issue. We were very parched. So this is what they looked like, but they took them off, but they were locked and we could never get water. So it was mainly because of COVID-19. It was just unsanitary. The buttons were a main spot of bacteria and the spout. So we wanted to remove the buttons completely, add some sensors so it would be motionless, you wouldn't have to touch it, and we would prevent people from putting their mouth on the spout.
So we sent out a survey to students and teachers. We got 207 responses. We asked about how much water they're getting and if like having the drinking fountains locked affects how much they're getting daily. And many said yes, including one said that their friends are more dehydrated more often than not now that the bubblers are locked.
And so our target audience would be anyone in any public building or any facility in a school that they don't have a water bottle to drink from, so that they don't become dehydrated throughout the day.
Okay, well, this was our original design. This was just like a mock-up to see how it would look like, and it's pretty accurate. I mean, we changed a few aspects, but it looks exactly like this.
So we made our basin like sloped so it doesn't catch as much of the mucus and it just runs down the water. And so the linear actuators are these things. They're raised on here because we thought about it going like covering more area, but in our final model, it's just a pole that holds it up.
This was our computer design. Instead of just cardboard, we based everything off of this, so it's pretty accurate. We made a couple of changes, but this is exactly what it looks like pretty much. You can see the holes for the sensors there and the spout, and this is the emitter beam that would move back and forth. And yeah, and this is also the timer. Okay, this is just another, you can see on the picture, but this is what it actually turned out to be. So we riveted it mostly together. We did a little bit of welding, but it's pretty sturdy. So.
And then what we also did about the basin is that when we put it in Inventor, we flattened out into AutoCAD, and then we were able to cut out the pieces on the laser, so we were able to get it nice and precise so that there would be no leaks into the basin.
There's
into
still
all of our
no
wires.
leaks. We still had lots of leaks.
Yeah.
So the purpose of the basin, just changing it, was so I have tougher time sticking to the sides, and there's no stagnant water like in the other ones. There's like kind of like a pool, and lots of water will sit there, and you can kind of see the marks it leaves when it's there for so long. So this eliminated that.
We also redesigned it so we could mount the linear actuators better.
So these are the linear actuators. They're what moves our sanitizing things back and forth. We bought them from Actuonics. Go next slide.
Essentially, only this part moves.
Yeah.
This moves back and forth, and we mounted everything off of that.
So this was the final thing. We mounted the stuff on top of that, and it runs back and forth. It takes about 40 seconds to go back and forth.
It only sprays one direction, so there isn't too much sanitization sprayed.
And yeah, they're the T16S mini track actuators from Actuonics.
And then the next thing that we implemented was the misters, and so we used tube hosing to go across our basin so that it would spray sanitizer onto our basin. And so we have it lifted above on a metal poles that we welded together so that it would clear the faucet head so it wouldn't hit it. And then as Matt said, as it goes back, it sprays, and then as it, actually in this picture, it's backwards. It's supposed to start back here, and then it's supposed to move forward and spray, and then as it goes back, it doesn't spray anymore, so we don't use excess sanitize that we don't need. And then we just used a hose kit that we cut up the pieces to make it shorter and to our needs.
This is what actually creates the missing, this pressurizes the missing points right here. We just mounted it in there and changed it a little bit, but it's just a stepper motor that just pressurizes those. So that's what it actually looks like. Lots of wires, and this caused us a lot of problems. Okay, well then these are just the stats. Instead of using a DC motor that would just have positive, negative, it has 4 coils, so it was quite complex to actually get working, and so we chose it because it's very it's precise. You can change the speed, where it is, and
So this is what holds our sanitizer. We just bought it off Amazon. It's actually a PC like liquid holder, and it connects to the stepper motor from there. The tube runs to the stepper motor, and the stepper motor sends it up to the linear actuators. And so that's what it looks like. It just holds the sanitizer. So our sanitizer, stored in the bottle that I just showed you, connects to the stepper motor. The stepper motor pumps it through all the way up to the linear actuators, and while the linear actuator going back and forth, it dispenses out the nozzles.
And so we wanted to implement a no-touch solution to our bubblers so that when people go up, they don't touch the buttons and they don't get all their germs on the bubbler. So what we first did is we wanted to make sure that there was some way to start the bubbler. So what we did is we have 3 sensors, 2 on each side and then 1 on the front. So we drilled little holes into the side of the basin. And so as you can see, there's one, and on the other side there's another one, and on the front there is. And so we have a 15 centimeter distance to where the proximity sensors can read you when you come up. And then after it undetects you, there's a 5-second delay before our sanitization process starts. So we just use proximity sensors from SparkFun, and they're just breakout sensors. And we also use the ones with the quick connect so that they're easy to connect with all the wires and communicate to our Blackbirds.
This is the sensors that we used. We ended up using 4 of them. We tried to use something that would be easy to just plug in and then have code and be easy to use. But these are the stats. You can detect up to 20 centimeters, and it's pretty accurate. So for what we needed for.
So this is the faucet. This is the original inventor model. This was the final model. So the sensor sits in the back of there, and through the little hole it reads out, and when you get too close to the water, it turns off the water and automatically begins the sanitation process to prevent people from sucking on the spout, because that's gross. And we use the same SparkFun proximity sensor.
We use a timer just to show how long you have to wait for the motion of the linear actuator to go back and forth. It's just like 7-second display. That's what it looks like. So these are the stats. You can just this was not that complicated. It was just pin out and
And so in a regular bubbler, there's a solenoid valve that controls the flow of the water. This one's push, so when you push the button, it would turn on the water, and then when you released it, it would go off. So we had to come up with a solution since we were implementing the no-touch part. So we had to order an electronical solenoid valve that would communicate with our sensors of when to turn and stop the water. The one part that we did come up with was the flow pressure. The filter did clog with the water that we were using because the school's water is not the cleanest, I guess.
So we implemented no touch to limit the possibility of skin-to-skin contact. So when people touch it, they could leave germs on there, and then when the next person comes, those germs get on their hands. So by having sensors for everything, you're not directly touching the bubbler whatsoever. Therefore, there's no direct bacteria transfer.
So this is the hard part, right here, programming and wiring. As you may know, water and electronics did not mix, and we had a couple of shorts. So we ended up using actually 5 Arduinos. We had 1 Arduino for every sensor. It was quite complex.
We didn't actually need 5. I broke one of the boards on accident, so we needed 5 after that.
Took the hard way around. But anyways, these just communicate with each other. These just have their appropriate sensor, and this is the main one that actually controls everything. It's just another picture. These are the cables that we try to use for the sensors. This is the valve you can see that controls the flow of water, the stepper motor, and yeah, lots of wires.
This is the power supply we used. It's, once again, like other groups used, an old computer that we just took from maintenance. And this is the 24-pin ATX diagram. So each we used the 12 volt and the 5 volt mostly, and then also the ground and the PS one. And
I did.
all right.
Oh my gosh.
It's like a video game.
All right, there we go. There.
So we used a lot of different things to try and get the water pressure good enough. I went to Menards and bought a garden pump. Didn't have enough pressure, so it was barely coming out of our faucet head, so we had to use an old sump pump. That got plenty of pressure. And we had to, all these adapters to get it to the 1/4 inch tubing we had. And yeah, it was like $20 at Menards. Put it together one day.
Works great though, so yeah. Here's a video. So, and then it takes nothing, it waits 5 seconds. Goes through.
So right now I'm holding the
The drainage.
the drain system,
The drain system.
because right before this video it broke. So that was another last minute thing we had to change. This was last night. This video was taken. So right now it's not dispensing any sanitizer. It's just going back to its home position, and the timer's counting down to when it gets back.
There we go.
Yeah, any questions?
How much code did you use?
A lot. A lot. There was 5 Arduino, so there must have been at least 100 lines of code. So most of it was actually we had to implement ourselves. So yeah.
So I just don't understand why I needed 5 Arduinos.
Okay, so we had a board that connected all the proximity sensors together, and then that went to the one blackboard, but I broke the pins on it, and so we needed 5 Arduinos instead to connect each one of the sensors instead of one board. So
Yeah, the way the sensors work, you can only have one sensor on each board, so we had to use a separate Arduino. So, yeah.
Okay, that makes sense then.
So I remember the one day you had that Arduino that got to 198 degrees.
that wasn't an Arduino, that was a stepper motor.
Oh,
Yeah.
did you like get a new one?
It was a motor driver, yes. It got very hot.
So did you replace it?
No, it's still cooking. It's still cooking.
Nice.
You could cook eggs on it.
Yeah.
I think you really addressed a real problem. I've always thought bubblers were gross, long before COVID. But I wondered if you tried to address the mouthpiece. You know, how sanitary is the mouthpiece after just with the bar just going across?
We have the sensor on top of it, so if you can't suck on it, because if you get too close, then the water just shuts off.
You don't sanitize it.
Yes, it is sanitized, but
The sanitize does go over it as it runs.
we could definitely change the design, but we just use the old one just to make it, you know, more easy. So.
Yeah, that also broke this morning. So we had to fix that also, and more time after school today. So that was fun.
Any other questions? All right, thanks guys. All right, we have one last survey for you to fill out. All right, as you guys are finishing up, I want to thank you for coming tonight. We had a great night and really a great year of projects. I'm really proud of the 5 different projects we had. Students did an amazing job. We had a lot of fun, a lot of hard work, and it really paid off. Hopefully you enjoyed seeing the projects tonight. Thank you for joining us. The students will bring their projects back outside to the Commons. You're welcome to talk with them. Otherwise, you are free to leave once you finish the survey. Thanks again for coming tonight.